Hey folks, my name's Nathan Johnston, and welcome to Lecture 22 of Advanced Linear Algebra. Today we're going to talk about orthogonalization, and what this is it's a procedure for turning an arbitrary linearly independent set into one that's orthogonal with respect to whatever inner product you're talking about. Okay, and the reason this is important is because we've shown earlier this week that there are nice things that you can do with orthonormal bases, but we haven't actually talked about how to construct them in the first place. So that's what we're doing today. We're constructing orthonormal bases, and as sort of an immediate corollary, we're going to show that yes, every finite dimensional inner product space actually does have an orthonormal basis in the first place. Okay, so we can do all these nice things that we talked about earlier this week. All right, so how does it work? How do we construct orthonormal bases of whatever inner product space we're working with? Well, the idea is you start off with just any old basis, okay? It doesn't have to be orthogonal or anything like that. So just start off with some basis, and we're going to turn it into an orthonormal basis, sort of one vector at a time, okay? So we're going to start off, focus just on V1. How do we sort of turn this more into an orthonormal set here? How do we turn it into an orthonormal basis? Well, for V1, all I'm going to do is I'm going to divide it by its norm so that now this new vector, this U1, has norm 1. Okay, so, and then I'm going to throw that as the first vector into my orthonormal basis, right? Okay, so U1 and V1, they're pointing in the same direction, but U1 has been scaled properly so that it can be part of an orthonormal basis. Okay, and now we just sort of repeat this procedure, except there are extra technical details when you get to the second and third and so on vector. Okay, when you get to the second vector, now we want to rescale it so that it has norm 1, but we also want to make sure that it's orthogonal to u1. We want to make sure that u2 is orthogonal to this vector that we just computed. Okay, and the way that you do that is before you rescale your vector, you subtract off a certain piece here. Okay, and really what we're doing, we'll draw a picture of this on the next page, but what we're doing is we're taking V2 and we're subtracting the piece of it that's pointing in the direction of U1, right? Sort of what's happening here is V2, it has some piece of it that's going in the direction of U1, and then some piece of it that's going just off in some other direction. And the inner product measures how far along V2 is going in the direction of V1. So if we subtract this piece off now it's like going none in the direction of U1. It's orthogonal to it. We'll draw a picture on the next page to make that a bit more precise. Okay, so that's all that we're doing at the top there. We're taking away the piece of we're taking away the piece of V2 that's in the direction of U1. And then the second thing that we're doing is we're rescaling that whole thing so that the resulting vector U2 has length 1. All right, and now for the third and fourth and so on all the way up to the mth vectors, we just do the exact same thing. You start off with the vector vk or vm or whatever it is, and then you subtract off a whole bunch of terms like this, one for u1, one for u2, and so on, one for all of the previous vectors that you've already computed, subtracting off the piece of vk or vm that points in that direction. Okay, and then you just rescale things at the end of the day. All right, so let's draw a little picture here. Okay, before we state sort of the full big algorithm in full generality. Let's draw a picture here in two-dimensional space. All right, so you start off, you've got your two vectors. It's two-dimensional space, so your basis that you start off with has two vectors, v1 and v2, okay? And I've drawn on the unit circle here. This is the circle with radius 1 here, okay? At the end of the day, I want to end up with an orthonormal basis based on v1 and v2, and because it's going to be an orthonormal basis, I need two things. I need the resulting vectors to have length 1, so they're just going to point at the unit circle here, and I need them to be orthogonal. Well, the way this procedure that we just described works is works one vector at a time. So we're going to start off by fixing v1, because v1 is not on the unit circle. So it starts off, it just rescales things. u1 points in the same direction as v1, except, hey, it's just been rescaled so that it's on the unit circle. It has length 1, it has norm 1. All right. The next thing that we do, this is sort of the more complicated step. Okay, the next thing that we do, now we're happy with U1, we've got to fix up V2. Okay, the first thing that we do to V2 is we have to fix its direction, right? This is not a 90-degree angle. They're not orthogonal to each other. So the first thing you do is you notice that, hey, V2, it's going in this direction a bit. It's going in the direction of U1 a bit, but it's also going in a perpendicular direction a little bit. Okay, so what you do is you subtract off the component of V2 that's parallel to u1. We're going to subtract off this green vector here, which is exactly the inner product of u1 v2 times u1, right? We're going to subtract off the component of v2 that's parallel to u1. And when we do that, we're going to be left with just this vector over here, which is perpendicular to u1. okay? And then after that, all we have to do is we have to rescale this vector over here so that it's on the unit circle, and when we do that, we're going to finally get u2. Okay, so that over here, this is our orthonormal basis of this vector space. Okay, so that's sort of the geometric idea of what we're doing here. Let's show the big theorem, okay? And this theorem, this method of orthogonalizing a set of vectors, a linearly independent set of vectors, it's called the Gram-Schmidt process, okay? So here's the setup. Here's the big precise theorem for what we're doing today. Suppose that you've got some basis of an inner product space B, or sorry, an inner product space V. Then we're going to find some new vectors based on these basis vectors here. So the first one, like we said before, we're just going to rescale v1 to get u1. Okay, and then after that, u2 up to un, those are a little bit more complicated, but all you're doing is you're taking, for every k, you're taking the kth vector and then subtracting off the component of that vector in the direction of u1, u2, u3, and so on, up to uk minus 1. So you're subtracting off the component of vk in the direction of each of the previous vectors that you've already computed. Okay, and then at the end of the day, once you've computed that whole big thing, you just divide by its norm so that you're renormalizing it so that, yeah, uk actually does have length 1. All right, and then the theorem says that, well, if you define all these vectors here, then yeah, the set that you get by compiling all of these guys together into a set, it really is an orthonormal basis of the inner product space that you started with. All right, so that's our big beast of a theorem for today. Let's see how we prove it. Okay, so to start off, we're going to actually prove a stronger statement than this theorem here. Okay, we're going to prove a stronger statement than just this. Okay, we're going to prove that not only is u1, u2 up to un that an orthonormal basis of v, but actually u1, u2 up to uk, that's an orthonormal basis of the span of the first k vectors from this basis for all k. Okay, so if I choose k equals 1, then u1 is a basis, an orthonormal basis of the span of v1. If I pick k equals 2, then u1, u2 is an orthonormal basis of the span of v1, v2, and so on. That's true for no matter which k I pick. So certainly it's true if I pick k equals n, which gives me the statement of the theorem. Okay, so how do I prove this stronger statement here? Well, what I'm going to do is I'm actually going to work via induction. Okay, I'm going to prove this statement by induction. Okay, and so start off, base case of k equals 1. We've got to show that u1, the set containing just that one vector u1, that is an orthonormal basis of the span of v1. Okay, and the way that we do that is just, well, it falls out very quickly from the definitions, right? u1 is a unit vector. Okay, great. So that part of the definition of orthonormal basis is satisfied. It's orthogonal to every other member in the set because there are no other members in the set. And, well, the span of these two vectors is the same because they're just multiples of each other. So yeah, the set containing just this vector really is an orthonormal basis of the span of v1. Great, we're happy with that. All right, next up we got to do the inductive step. So we've got to show that if this statement right here is true for a particular value of k, then it's true for the next value of k as well. Okay, so what I'm going to do is I'm going to fix a particular value of k and assume that the statement is true for k minus 1. Okay, so I'm going to assume that u1, u2 up to uk minus 1, that's an orthonormal basis of the span of v1, v2 up to vk minus 1. Okay, now my goal is to then show that this same statement is true if I have a subscript k here and here. In other words, if I increase that final subscript by 1. Okay, so how do I do that? Well, the first thing that I'm going to do is I'm going to go back and clear up something that's maybe not completely obvious from this theorem. There's a potential problem here. What if this vector up here on the top was ever the 0 vector? Then I'm doing something that's not allowed here, right? If this was the 0 vector, then I'd be dividing by the length of the 0 vector, which is just 0. I'd be dividing by 0 on the bottom here. So before I can really do anything else, I've got to rule that out. Okay, so I'm going to start off by showing actually that this vector here is not the 0 vector. All right, so the way that I'm going to do that is, well, remember that set B that you started off with, it was a basis, therefore it was linearly independent, and therefore vk is not in the span of v1, v2 up to vk minus 1, right? The set containing v1 up to vn is linearly independent, so is the subset set containing v1 up to just vk. That's a linearly independent set, so none of them are in the span of the others. All right, But span of v1 up to vk, that's just equal to span of u1 up to uk minus 1, right? These spans are the same because by the inductive hypothesis, I'm assuming that this u1 up to uk minus 1 is an orthonormal basis of this span here. Okay, so these two spans are the same by inductive hypothesis. All right, so the upshot is vk is not in this span here. So in particular, vk cannot be written as a linear combination of these k minus 1 vectors. All right, well, if vk can't be written as a linear combination of those vectors, then we know right away, great, this quantity here is not equal to 0, right? Because what is this sum over on the right? Well, it's a linear combination of u1, u2 up to uk minus 1. All right, well, vk does not equal that linear combination, so the difference of them cannot equal 0. All right, so what that tells us is that, yeah, this Gram-Schmidt procedure, it at least makes sense. We can define these vectors. And actually, furthermore, it tells us that the length of these UKs, it's going to equal 1, right? Because again, if you look at how these UKs are defined, well, I'm taking some non-zero vector and dividing by its norm. So it's going to have norm 1 now. All right, so great. We've pinned that down. These vectors make sense. And yes, they have norm 1. So that's the first piece that we need to prove. Next piece we need to prove is orthogonality. We need to show that no matter which two members of this set u1 up to uk that I pick, they're orthogonal to each other. Okay, so what I'm going to do, well, by inductive hypothesis, I'm already assuming that u1 up to uk minus 1 is an orthonormal basis. So I'm already assuming these guys are orthogonal to each other. So I just need to show that uk, if I throw in one more member, that's orthogonal to all of these guys that are already in there. So I need to show that uk is orthogonal to u1 and u2 and so on. All right, so what I'm going to do is I'm going to let j be some subscript that's less than k, and then I'm going to compute this inner product here. And my goal is to show that equals 0. All right, so how do I do that? Well, not much I can do with uj, it just is what it is. But uk, I've got a formula for that. Again, let's just go back to the Gram-Schmidt sort of theorem box here. I've got a formula for what uk is. So I'm just going to plop that formula into this inner product. And I get this big ugly beast here, uj inner product with big ugly mess. All right, and now we're just going to use properties of inner products to simplify that. In particular, if I start off with linearity in the second component of the inner product, I can split up this whole big chunk here on the outside of this inner product, right? So I'm just going to get uj inner product vk, that's where that's coming from, and then subtract off uj is going to get inner producted with this ui, so that's where that term's coming from. And then the sum of the ui vk's, well, those are there. And then this whole quantity here is just coming out on the bottom, right? This is a scalar, so I can pull it outside of the outer inner product. And now I just have this beast here after pulling as much out of this outer inner product as I can. Okay, but now I can look at some of the terms in this big ugly sum here, and I see that actually a bunch of them go away. If I focus on this term here, well, this is the inner product between two things that I'm assuming are in an orthonormal basis, right? Again, the inductive hypothesis is that the set of all the u's up to the k minus 1th are in an orthonormal basis. Okay, so this inner product equals 1 because the norm has to equal 1 if I equals j. And that inner product there equals 0 otherwise because they're orthogonal to each other. So what happens is this sum here goes away. The only way that this term in the sum is non-zero is if j equals I. Okay, so this subscript here has to equal j. I has to equal j. All right, so that simplifies down. The sum goes away, and the whole sum just equals the inner product of uj with vk. And now we're golden, right? Because now just look at this numerator. I've got the difference of two inner products. Those are the same inner product. So I just get 0, which is what I wanted. Okay, so yeah, uk really is orthogonal to all of the previous uj's. And that's actually all that I need. I'm done at that point, okay? Because what I've shown now is that the set containing all of the u's up to the kth one, well, that set is mutually orthogonal. All its members have length 1. And, well, furthermore, I mean, it's a set containing k vectors that all live within the span of, sorry, just trying to find, that all live within this span here, that all live within the span of v1 up to vk, okay? Well, so if it's k vectors that are mutually orthogonal, they're all non-zero, they live within a k-dimensional vector space, well, therefore, it must be an orthogonal basis, right? That was one of our observations that we made in the previous class. So we're done at that point. All right, so that gives us the Gram-Schmidt process. And an immediate corollary of it is, well, Gram-Schmidt process says, hey, here's a method for constructing orthonormal bases out of any old basis. Well, we already know that every finite dimensional vector space has a basis, so now we can convert that into an orthonormal basis, and we get this corollary that says, well, now every finite dimensional inner product space has an orthonormal basis, okay? So it's not just you can always find a basis, well, you can actually always find an orthonormal basis, which is, in a sense, sort of the nicest bases that exist. Okay, they're sort of bases, but even better behaved. Okay, so let's go through a quick example of actually implementing the Gram-Schmidt process and actually constructing an orthonormal basis in inner product space where it wasn't obvious how to do this before. So we're going to return to this inner product space P2 negative 1 to 1. Remember, this is the degree less than or equal to 2 polynomials on the interval from minus 1 to 1 with respect to the standard inner product, or just this integral inner product. We made the note earlier that the standard basis is not an orthonormal basis with respect to this inner product, okay? So it's not obvious how to construct an orthonormal basis, okay? But we're gonna use the Gram-Schmidt process to do it. And here's how it goes, okay? You start off with any old basis of whatever vector space you're working with, okay? So in this case, well, let's just start off with a standard basis, okay? 1xx squared. It's not orthonormal, but that's okay. Gram-Schmidt will fix it up. Work one vector at a time. So start off with the vector 1, the function 1, divide it by its length. So we got first compute its length. And be really careful here. It's tempting. It's so tempting to say, oh, the length of the function 1, that must be 1, right? Well, let's work with the definitions and be careful here. What does this mean? The length, or sorry, the norm of the function 1 is the square root of 1 with itself. Okay, well, of the inner product of 1 with itself? What is the inner product of 1 with itself? Well, it's the integral of 1 times 1. So it's just the integral of 1 on the interval, so from minus 1 to 1. Okay, well, what is this integral here? Okay, well, integral of 1 is just x, and then you plug in the endpoints, you end up with root 2, not 1. So be really careful here. The length of this function, the norm of that function, is root 2. It's not equal to 1. So what is the first vector in our orthonormal basis? Well, it's the first vector in our any old basis divided by its norm. So it's 1 over root 2, the constant function, 1 over root 2. All right, great. That's the first member of our orthonormal basis. Let's go on to the other ones. Okay, so let's try to construct U2 now. And here I'm just copying down the formula from Gram-Schmidt. Here's what U2 is. So there's some pieces that we have to compute here. We have to compute this inner product. Again, that's going to be an integral. And then we have to compute this norm. And again, that's going to be an integral. Okay, so inner product of U1 with V2, let's start off with that piece. Well, that's the inner product. We just computed U1, so that goes in the first slot. And V2, that's the second member of the any old basis that we started with. So that's X, that's where that's coming from. Okay, so that's what V2 was. Okay, and now we just plug that into the formula. What is the inner product? Well, it's just the integral of the product. This inner product is the integral of the product, so it's just X times 1 over root 2, and then you integrate it on the interval. Okay, and then you just compute that. It's going to be 0 in this particular case, actually. I mean, you can do the computation sort of explicitly if you like, but here you're integrating an odd function over a symmetric interval, so you know right away it's going to be 0, actually. All right, so that's the first piece. Now we need to compute the norm of the denominator here. Well, we just computed that this inner product is 0, so this part of the term goes away, and we're just left with what is the norm of V2? Well, again, V2 is X. It's the second member of our original basis. Inner product with itself, then square root at the end of the day. We just plug that into the integral. X times x is x squared, so that's what we're integrating. And then you just compute, okay? Integral of x squared is x cubed over 3. Plug in your endpoints, and you just end up with root 2 over 3 at the end of the day. Okay, and now we know what these inner products and norms equal. Just plug everything back into this formula. And you find that the second member of your orthonormal basis is just root 3 over 2 times x. All right, so now we've got 2 members of our orthonormal basis. We still need one more, right? We need to compute U3. We have one more to go. All right, so again, what is the formula that we get from Gram-Schmidt? Well, now it's just this big ugly beast, okay? So you start off with V3, and you have 2 components that you gotta subtract off this time. So now we've gotta compute this inner product, and then after that, the norm of the thing on the bottom. So we've got 3 integrals to compute this time. Start off with the first inner product, U1 with V3. And again, you just integrate their product. U1, we computed that up above. That's 1 over root 2. v3, that's the third vector in the original basis, that's x squared. So the product is x squared over root 2. And then you just compute that integral. This is just standard calculus stuff, so I skipped over it. You're going to get root 2 over 3. All right, next inner product that we've got to compute is u2 with v3. Okay, so inner product of u2 with v3, what is u2? Well, we just computed it. It's root 3 over 2 times x. You plug that in there. What is v3? Again, that's x squared. Okay, and then their product is going to be square root of 3 over 2 times x cubed. And here we got something similar to what happened up above. Here's an odd function. We're integrating it over a symmetric interval. We're going to get 0 at the end of the day. All right, and then last but not least, we need to compute the norm of the thing on the bottom. Well, one of the terms on the bottom ended up equaling 0, so we've just got the difference of the other two. The norm of it is the root of the inner product of it with itself. So the reason we've got the squared here is because it's this thing inner product with itself. So it's the product of that with itself. So it's going to be all squared. And then you integrate it, and then you square root it. And again, this is just calculus. You're just integrating a polynomial, so there's nothing fancy here, right? It's just kind of ugly. And you end up with root 8 over 45 at the end of the day, which we can just simplify a little bit as 2 root 2 over 3 root 5. All right, great. Now we know all of these inner products that we need, so we just plug everything back in here into our formula for u3. And what do we get? Well, after you simplify a little bit, you get u3 equals root 5 over 2 root 2 times 3x squared minus 1. Okay, so that's the third member of our orthonormal basis. All right, and that's basically it. Okay, now we've computed u1, u2, u3. You just throw them all together into a set, and you end up with an orthonormal basis of the inner product space that you started off with. Okay, so if you want to sort of double check your work and make sure you've done things right, compute the inner products of these functions with each other. You're going to find that each pairwise inner product is equal to 0, and each inner product of a function with itself equals 1. So it really is an orthonormal basis of that inner product space. All right, awesome. So that does it for lecture 22 and for week 5. So I will see you soon for lecture 23.